you have to haul it by truck, you're going to want to consider that truck transportation impact that Tom was talking about. Also, as Tom mentioned, there's a lot of push at various times, often from people outside the pavement industry. Well, why don't we recycle? We've got a bunch of this. Why don't we stick it in the asphalt mix? Why don't we recycle it, take it out of the landfill, and stick it into the road? And the question that, as pavement professionals and as decision makers, that we need to consider is that a one-time recycling of that material into the asphalt mix, which then stops us from continuing to recycle that mix, put it back into warm mix products as we talked about here? Can I run that material in 10, 15, 20, 40 years back through an asphalt plant without problems? That's one of the main considerations that we need to look out for those few cases where recycling is not the best idea. There is work out there looking at substitutes for petroleum asphalt, and I think a key thing is that in most cases these are not substitutes, but they're being looked at as asphalt extenders, things that we would mix with the asphalt to create improve the properties and reduce the amount of petroleum in the asphalt binder. These primarily are biobinders from non-food plant or animal waste, and there's fermentation, fast pyrolysis, and gasification processes. Each has its own environmental impact. There's a lot of work going on out there, so this is something to keep an eye on in the future. There's also been work off and on over the last 20, 30 years with the use of sulfur as a substitute or as an extender for petroleum asphalt. So some of the strategies for improving the sustainability of asphalt mixes include, and I think that I've put these in sort of my opinion of rank order. Other people may have other opinions, but first of all, to increase the material performance and the time between future maintenance and rehabilitation treatments. If we can extend the life of an asphalt pavement or an asphalt mixture by the things that we do in materials design and particularly in construction quality, that's an easy way to reduce the impact. If we can increase the life by 20%, that means that we reduce the amount of material that we're using by about 20% as well over a life cycle. The next thing we can do is work to reduce the amount of virgin asphalt binder and aggregate and polymer in the mix. Use the polymer where it really has a benefit. Use more wrap. Look at recycling tire rubber where it helps us with performance, where we have a net benefit. Consider the use of RAS. Again, use additional additives where the performance increase warrants the additional environmental impact. We also, as Tom talked about, aggregate, same is true for asphalt mixes, reduce the materials transportation. Use locally available materials where we can get similar performance or where we can find a way to offset a reduction in performance by our pavement design or how we're handling and designing the materials. And also look at in-place recycling eliminates most of the materials transportation impact. 2 and 3 are really based on not taking a big hit on pavement performance. If we're doing those and we take a big hit on pavement performance, our net impact is going to be bad rather than good. Some real-world considerations, understanding sustainability goals of the organization. An example was given for the Illinois Tollway. They set some clear goals for what they were trying to do. There's a number of impact categories, environmental impacts that you can consider. Once you define that, then look at the trade-offs to reduce impact, but taking into account that life cycle consideration. So we need to consider the environmental impacts of material decisions, the effects on performance, and the replacement frequency, transport distances, and our ability to almost perpetually recycle many of those materials. A question to ask, are our current specifications limiting the use of lower impact materials? Are we really getting an improvement in performance, or are we setting high specifications for some of these materials where the overall impact on performance is not that great, but we could actually have a pretty good impact on sustainability. So reviewing specifications and design procedures to look at where you can change those with minimal impact on performance, but potentially allowing greater use of recycling and locally available materials. Then our next subject is going to be pavement design, looking at pavement design so that we can make the best use of the lower impact materials without compromising performance. An example of this, not necessarily a typical example, but just an example, is a state agency with a mixed design procedure that was intended to minimize the risk of rutting by keeping the binder contents low. And the question that was evaluated here was, what's the impact of changing the gradation and increasing the binder content in the mixed design to increase the cracking resistance and therefore increase the amount of time between needing to do preservation treatments or rehabilitation. So performance-related testing was used to evaluate the stiffness, the fatigue cracking resistance, and the rutting resistance of using the same materials but changing the mixed design. And then mechanistic empirical design was used to evaluate the effect on the pavement thickness required for the same performance for the lower binder content under the old mixed design system or with a somewhat higher binder content under the new mixed design specifications. And the result was that the risk of rutting was increased, but it was way over-specified previously, and the risk of rutting was still acceptable with the increased binder content in general. However, by increasing the fatigue resistance of the material, we could reduce the thickness and still get the same cracking life. So then the question was, what's the net impact of increasing the binder content but being able to design a somewhat thinner pavement? So apologize for the metrics here, but by increasing the binder content by 5.5%, from 5 to 5.5%, the mechanistic design indicated that we could reduce the thickness. This was there are a number of examples but were run, but for an example pavement from 4 inches or 103 millimeters to about 3 and a quarter inches, about 84 millimeters. So about an 18% reduction in the thickness. What this does is overall reduces the amount of mix needed, and even though we increased the binder content, the amount of total binder needed was reduced from 44 cubic meters to 36 cubic meters. So this is the kind of analysis where you may get a result that you were not necessarily looking at. Okay, some future directions and emerging technologies. We're expecting a reduction in material quantities used per year through improvements in mixture design and construction practices, the new technologies of warm mix, and the strategic use of polymers and rubber and other modifiers, increased use of performance-related testing and specifications to fine-tune these mixes, greater use of recycled materials, particularly RAP, greater use of locally available pavement materials, and longer term, the potential for use of alternative binders. Okay, switching subjects to pavement design. Some of the key issues for pavement design are surface performance, particularly smoothness, which affects vehicle fuel use and maintenance, has very big cost implications as well as environmental implications. We need to consider the life cycle smoothness, not just the initial smoothness, and the importance of smoothness increases as the amount of traffic using the road increases. Another issue is design life selection. Longer life usually means lower life cycle cost and impact, but that should be evaluated. Depends on the context. It also means a higher initial investment in terms of cost and environmental impact. And we should consider some different end-of-life alternatives in that as well. In the design life selection, what are we going to do with the pavement when we reach the end of that life? Pavement type selection is an issue. It impacts every phase of the pavement life cycle. We need to look at the relative sustainability of different pavement types is going to depend on the location, the traffic, and the available materials. We need to look at the interaction of construction and material selection with our pavement design, considering designing so that we can maximize the probability of getting high-quality construction. There will be some discussion a little bit about work zone traffic delays, and then integrating our pavement design with our construction quality requirements. And thinking again about how do we think about the end-of-life recycling strategies in our initial pavement design. Mechanistic empirical design methods really give us a leg up on being able to do relatively rapid evaluation of all of the different things that we've been talking about with regard to materials as well as pavement design. We can characterize materials with increased recycled content, with lower environmental impact, changes in mix design as in the example we just looked at, use of locally available materials, characterize those materials, run them through the mechanistic design, and get a first idea of what the impact is going to be on our performance. We can similarly characterize materials with improved construction quality, such as compaction, better compaction, reductions in variability, and making sure we get good bonding between the layers, and evaluate those impacts of changes in specifications.
Nice.
And we can also look at different kinds of pavement structures and fine-tune our pavement structures for the specific climate, traffic, and subgrade that we're dealing with on a given site. One of the things that we should consider, this has to do with pavement life selection. This was an analysis that was done looking at some, a current 20-year design standard going to a 40-year design standard, and just for analysis purposes going to a 100-year pavement. And this is some of the analysis that can be done with regard to looking at things that have a higher initial impact, and then trying to understand how long does it take to get back to the same point in terms of the impact as if we had done something with a lower initial impact. So in this case, the 20-year design had a lower initial impact, but we had to do more frequent, the analysis showed more frequent maintenance and rehab resulted in, over the longer life cycle, a much higher environmental impact. The 40-year design had a reduced environmental impact shown in red here, and that paid back after a relatively short amount of time. The higher initial impact of the 100-year pavement didn't really get paid back till way out in the future, which decreased the chance that we were actually going to get a payback. So the point is that different changes can be looked at, initial impact versus life cycle impact. The overall process for considering sustainability in pavement design is outlined in the reference document. I'm not going to go through all the details. The basic first part here is basic mechanistic empirical design. The next step is to, based on the structure that you're evaluating, determine the life cycle cost, select your pavement design, and then go through, look at alternatives for optimizing the environmental impact. So the general recommendation is similar to what the Illinois Tollway was shown to be doing. Focus on your cost first and then optimize your environmental impact to arrive at the final solution. There's a number of different pavement types. Here we can see, I'll just go through a few of these. All of these are alternatives that can be considered. Each one should be looked at in terms of some potential trade-offs. We have full depth asphalt, where all of the layers are asphalt bound on a compacted subgrade versus a conventional asphalt pavement, where we're using granular layers to help carry the loads. Example of trade-offs would be the full depth asphalt would have a higher, we're using a higher impact material for most of the structure, but on the other hand, potentially we can reduce the overall thickness of the pavement substantially, which may result in a net benefit in terms of environmental impact. So, and then we can further, if we're using a full depth asphalt as an example, we might be able to offset a greater amount of that impact by using a high wrap content in the deeper layers in the structure. Some other types of pavements we can consider light stabilization, as shown on the left, which can substantially improve the performance of the aggregate layers under the asphalt. We can cement treat the materials and then use a granular base called an inverted pavement, used quite a bit in Southern Africa and some other locations. We can use composite pavement as a new pavement structure, where we build a concrete pavement and then use asphalt on the surface, which can help us thin down the concrete. This is the subject of research in the SHARP R21 project. Or in many countries, or in cases where we don't have a lot of access to good crushed aggregate materials, we can use semi-rigid pavement, where we cement stabilize the base and then use asphalt layers on the surface, which can also help us thin the pavement down for very heavy axle loads. Looking at rehabilitation, most of the time on asphalt pavements we're doing structural asphalt overlays. We can also overlay with concrete, bonded or unbonded concrete overlays. Generally, we're going to use a bonded concrete overlay on asphalt. We need to compare the life cycle costs for these, and we need to compare the environmental impacts for each of these, and look at alternatives within each of these strategies to reduce the environmental impact. Our surface choices, again, we're primarily looking for rut resistance and skid resistance. In our design process, we can consider the use of dense graded asphalt concrete. We can look at high friction materials such as chip seals and microsurfacings, primarily used as preservation. One thing to think about, recent work we've seen is considering non-motorized users for some of these surfaces as well. SMA can be used for noise and durability and friction. We can also look at open graded asphalt courses for noise, splash and spray, and friction. We can see on the bottom right here on the left hand side an open graded asphalt that is dropping the water off the surface, and a dense graded asphalt on the right where the water has to flow across the asphalt, and a reduction in spray that occurs from using the open graded asphalt. And there have been a number of improvements recently and upcoming in open graded asphalt mix design to improve their durability. This is an example of asphalt concrete tire pavement noise performance. And on the x-axis, we have the onboard sound intensity in decibels, which is the noise increasing to the right. And then this is looking at the performance of about 60 surfaces over 15 years. And we can see that the dense graded asphalt will have a higher noise, but we can reduce that noise quite a bit by going to open graded friction courses. We get some improvement even from gap graded rubberized mixes. And in this study, the best performer was rubberized open graded mixes, which maintain their durability and keep that noise benefit for quite a while. This is an example that can, and the type of thing that can be evaluated. An alternative that is primarily used right now for parking areas and low light traffic vehicle pavements is porous asphalt pavement. In porous asphalt pavement, we are making all the layers in the pavement permeable, not just the thin open graded layer on the surface, but the asphalt's permeable, And then we have open graded granular layers where we can store the stormwater and then infiltrate